Yesterday we talked about, or yesterday, whatever, 2 days ago, we talked about solving for systems of linear equations. And we started to transport our system into matrices so that we would have an easier tool. We'll have a tool to, a means for solving for these things. And what I wanted to do was first try to take a look at some systems of linear equations and then see how they would look like in matrix form. And so let's start off with just a two-dimensional 3x minus y is equal to 4 and 2x plus y is equal to 1. So for something like this, in order for us to solve for this, we remember techniques from algebra where we would either solve for one of the variables or eliminate one of the variables or do some sort of substitution. So at this point, I'm not too interested in solving for this. I'm just interested in transforming this into a matrix. So it'll be 3, -1, 2, 1. Now, if we stop there, we would consider this our matrix of coefficients. And we have 2 equations and 2 unknowns, so our matrix would be a 2 by 2. But since this is a system with equal to some constants, we're going to include this other row or other column. And we usually use a divider to separate them, and we call this an augmented matrix. So this augmented matrix is going to be our key, our step-by-step process to solve these systems. All right. Now, we don't know if we ran into some special matrices, but let's take a look at an example of a system that looks like this. I'm going to make it up here. X minus y plus z is equal to 1. 3y minus z is equal to 2, and z is equal to, see if I can make this nice, 4, 6? I was going to put 4. Does that work? Is it 4 nice? 4 would be nice too, right? So this is a matrix that, or this is a system that is a nice system for us if this was given to us from the beginning, because we can easily solve for this. We don't have to do much work, right? All we have to do is take since we already have our z here figured out, we could take that and do what they call back substitution, is to work backwards. So from this information, you would say 3y minus 4, because that's what z is equal to 2, and you get y is equal to 2. And then from there, you get x minus 2 plus 4 is equal to 1, and so x is equal to -1. All right, so there's an advantage if you have this, or I guess it would be more like luck than an advantage. And there's something interesting when you transform this into a matrix, into an augmented matrix, and that is that this would look like, what would it look like? A staircase, right? So 1, 1. Since there is no x here, we have to assume that there was an x there, except the coefficient was 0, so that made it disappear. So 0 times x, 3 times y, minus 1 times z. 0x, 0y, and then 1 times z. And the interesting part or aspect of this particular matrix is that there's that staircase idea that it's zeros in the lower part, lower left part, lower left, lower. Let's just say lower. There's zeros in the lower part of this. This, by the way, has a special format called upper triangular matrix. And this is an upper triangular matrix because from the diagonal and everything up, and up from the diagonal would be up and the right. That would be northeast, right? Anything from the diagonal onto up is non-zero, and everything else is zero. And just so we know, I just use the word diagonal, but if you didn't know that, it's literally the diagonal. I don't know. It's the diagonal going down. So these are aspects of matrices that we're going to use over and over again. Things that are upper triangular, we want to know stuff about the diagonal. Those are things that we're going to use. All right? So this will get us going. I wanted to do one more example. So let me do one more example real quick. And that is if you had x1 is equal to 1, x2 is equal to 2, x3 is equal to 3, x4 is equal to 4. And I would normally write it like this if it was all if I had x2s, x3s, and x4s for the first equation, I would write down the rest of them, but I would line them up so that the variables are lined up. Makes it easier for people to see. But anyways, if your system looks like that, how's that going to look like in your augmented matrix form? It's just a diagonal, and the diagonals would be 1. Well, if you have this, right, and the idea is for a system, you would be solving for the variables, in this case x1, x2, x3, x4. It looks like it's already solved for. It's already there. So x4 is equal to 4, x3 is equal to 3, x2 is equal to 2, x1 is equal to 1. So this is a very nice system where it's already solved for us, and we don't have to do any work, and then we can just give the solutions. But what I wanted to show was how the corresponding matrix looks like. And if you have a corresponding matrix that looks like this, well, that transfers back to a system that looks like this, in which case you have all the solutions. All right, vocabulary words that we're going to learn today. This is called reduced row echelon form. This is called, the upper triangular matrix where they have zeros is just a regular row echelon form. So the difference between the two is that the reduced one has only diagonals. Now these are special cases where it comes from square matrices, right? But there's some other cases that we're going to be dealing with where the matrices are not going to be square. So the idea of a diagonal is still going to be from the upper left-hand corner going down in the diagonal way. And if you don't have a square matrix in your matrix of coefficients, then your diagonal is going to be interrupted in a certain way. So we'll take a look at those special cases. Okay, questions? All right, so let's take a look at some of the important aspects of this that we're going to need. I think I took a snapshot of this in our last class. A matrix is in row echelon form if it satisfies the following properties, and I showed you an example of row echelon. And then what happens is that if you had an original system of linear equations, from that system, we kind of did solve for a system where we added something to the first row, or we multiplied the first row by something and added to the second row, or something like that. And then I tried to pull that analogy from a regular system of equations to the matrices. And now that we're dealing with matrices, I think a lot of times it's easier to look at the matrices instead of all those coefficients along with their variables. So for matrices, we have what's called elementary row operations. So going from a system of equations to a matrix and then performing these elementary row operations will not change your system, the solution to your system at all. And what happens is that when you do these row operations, you have it in either the reduced echelon form or the regular row echelon form. You can back substitute and solve for your variables so you can find your solution. So let's take a look at our simple example over here. Where we created this matrix. If we go through the reduction process and try to write this in row echelon form, we're stuck with using those elementary row operations. But if we just use them, and we can reduce it kind of easily. Oh, this one's not a nice one. Anyways, so what I'd like us to do is to take our steps to have this in row echelon form. And since this is only a 2 by 2 matrix, the augment, I don't usually count the augmented part as part of the matrix, but since this is a 2 by 2 matrix, we only need to make one of the things equal to 0, and then it'll be in row echelon form. And so we could do this one of two ways. We can switch the order, because that's an elementary row operation. If we switch the rows, that's still going to be valid. We can multiply a row by something, or we can go ahead and do this one where we add a multiple of the first row to the second row. So let's do that. And to add a multiple of the first row to the second row to make this 2 equal to 0, what do we need to multiply 3 by to get negative 2? You understand my negative 2/3? So we could say we're going to take row 1, multiply it by negative 2/3, add it to row 2, and then you get to replace row 2. That's kind of long-winded, but it's kind of like what I like to see. So this is your elementary row operation step. And what that's going to give us is a no change in the first row. But the second row now, if we multiply 3 by 2/3 and then add it to 2, we get 0. If we multiply this by 2/3, this will be positive 2/3. Add it to 1, that would be 5/3. And then this would be 8/3 plus 1. Subtract negative 8/3 plus 1. Negative 5/3. Okay. And now that it's in a reduced or row echelon, it's not reduced, it's just plain row echelon, we can transform this back into a system. 3x minus y is equal to 4. 5/3 y is equal to negative 5/3. And then we can go ahead and solve for y by doing a back solve or back substitution. Yeah? Yeah, it would be nice to not use fractions, but you may not have a choice. And in some of these cases, you won't have a choice. You'll just have to deal with fractions. Okay? So from here, you can go ahead and finish this, but let's do something else, since I did introduce the idea of reduced row echelon versus row echelon. Reduced is to take it a step further and make the coefficients, the leading coefficients, equal to 1. And so we could take advantage of some more simple basic elementary row operations to do that. So let's continue on with this matrix, and let's say the leading coefficients. So for each row, the first non-zero number that you see is called the leading coefficient. First non-zero number in each row is called the leading coefficient. So, for example, if we take the second row and multiply it by 3/5, thank you. If you take the second row and multiply it by 3/5, and then replace the second row with that new row, that's an elementary row operation. It's multiplying a row by a non-zero constant is an elementary row operation. So we can do that here. 3, -1, 4. Multiply this by 3/5, we're going to get 1, and then we're going to get -1 for there. We can also multiply the first row by 1/3, right? What's that going to do? That's going to give us a 1, -1/3, 4/3. Is this reduced row echelon now? What's wrong with it? The -1/3 is still a bit of a problem, because I think we defined reduced row echelon to have just numbers in the diagonal, ones in the diagonal as a matter of fact, and zeros everywhere else. It has to be 1, yeah. So to complete this, what do we need to do? To complete this, what do we need to do? Yeah, how? So some constant times row 2. What are we going to add? By 3? So if we take row 2, so a third, if you multiply this by 1/3, 0 times 1/3 isn't going to do anything. Notice that? That's important. This is going to go away, and then 0 or -1 times 1/3 is -1/3. 4/3 minus 1/3 is just 1. So there you go. Now it's in reduced row echelon form. And if you were to rewrite this as a system, you're going to get x is equal to 1, y is equal to -1, and there's your solution. Okay?
So this only talks about the non-augmented part.
Yes, the augmented part is just the tag along. Okay? Any questions? It's always nice to see easy problems. Your real problems are going to be a lot harder than this. You knew that. And if you think this is hard, dang. Sorry. So, row equivalence is just saying that if you change any of those rows by using the elementary row operations, then your system is not going to change. The matrices are what's called equivalent. So this definition and theorem combo here talks about that sequence that we just did of matrix. I'm going to go back over here and copy a bunch of things. Sorry, this is taking longer. Let's see if this works. So all these matrices, I don't know which the order. This is the last one. This is the second one. Third one. So all these matrices were obtained from the previous matrix by some elementary row operations. So because of that, then all these matrices are all equivalent. And the very row reduced echelon form is going to be the same for any elementary, for any row equivalent matrix you have. So all these matrices are equivalent or row equivalent. I guess there's going to be another equivalent term later on. which means for us, what that means is that we can use this row reduction to solve for systems of linear equations, and that's the whole point in doing this. Because you make your changes to your equations or you make your changes to your matrices, as long as it's an elementary row operation, then it's all going to give us the same result, regardless of how we get there. And that's what we like in math, is you can get there a bunch of different ways and you get the same result. Okay? All right. So there's some more examples that we can do, but let's take a look to see if there's an example where it's not going to be a perfectly square matrix. What? I don't know. I'm not different. All right, let's do number 28 maybe. Before we get too far with like really nice and easy ones, we should take a look at an example where it's not a nice square matrix and it doesn't all reduce to a nice row echelon form. So this one has 3 equations and it has 4 unknowns. And we want to know if we can solve for this and find solutions for this. So let's first thing we want to do is write it into a matrix. And remember that the variables, there's 4 variables, so your original matrix will be a 3, that's 3 equations, and 4 columns, and then you augment it with a constant terms, and then that's going to be 5. So there's the 4, and then here's the 1 on the end. And just be careful of the negative signs. There are negative signs in the coefficients, then you got to make sure you incorporate that as a negative sign in your matrix. So there's a lot of different ways to get to our row echelon or reduced row echelon form, and so it's really up to you how you want to take it there. So you could do different things if you want. Let's see, I'm going to start off by I see that there's 2 and 2 here, so I'm going to take row 2 and subtract it from row 3. I guess I should row 3 minus row 2. That goes into row 3. That'll get my first 0 down in the denominator. So this is like multiplying by -1, right? So this would be 0, -1 plus 3, 2, -1 plus 1, 0, -1 minus 1, -2, -1 plus 2 is 1. Okay, maybe I should write it carefully here. So the official way to do this is you take the row that you're going to change, and then you add a multiple of another row, a different row. So I think I did that one the way this was. I haven't been doing it that way. So I'm going to take my row 3, and I'm going to add a -1 to row 2 and add it to row 3, and that's going to be my new row 2, or row 3. What? Yeah. I'm going to take my row 3 and I'm going to add it to -1 times row 2, and that will replace my new row 3. So the next thing probably to do is get rid of this 2 over here. So I'll do that in this next step. I'll take, I want to change row 2, and then by doing that I will add 2/3 or 3/2. 2/3 times row 1. So subtract, so that should be a negative. Add the negative multiple. So that's going to replace my row 2. I'm trying to go with what the book says, but I don't really think like that. I would normally write it like a little bit differently. But anyways. All right. Think like the book. Think like the book. 3, 3, 1, 0, 1 for the first row. The second row is going to change now. If nothing else, I know the first one's going to be 0. This would be -2. -2 plus 1 is -1. This will be -2/3. -2/3 plus that is +1/3. Start those fractions going. This is going to be 1. And -2/3 plus 1 is 1/3 again, right?
Oh yeah, it's going to get real with this fraction.
Right. Okay. So now, so the next step is this 2 down here. So maybe I should have been highlighting what I wanted to get rid of. So I get rid of that. So that's gone. Now I want to get rid of this. So that's gone. We got this. And then it looks like we just want to see if we can knock this one out. The 2. Need longer arrows here. So for that one, I probably want to multiply the second row by +2, and then add it to the third row, and then replace my third row. And so the first and second row don't change. The only thing that changes is this third row. So if nothing else, I know that that's going to be a 0. Multiply this by 2, that would be 2/3. Add it to 0, that's 2/3. Multiply this by 2, that will be a 2. Add that to that is 0. And multiply by 2 is 2/3 plus 3/3, 5/3. So at this point, we are at the row echelon form. So the idea is that we're supposed to be able to back solve, but this is a case now where we're not able to back solve because, well, maybe we are. Let's see how far we can get out of this. So now your equation or your system, let's put it over here. Your system will look like this: 3w plus 3x plus y is equal to 1. Negative x plus 1/3 y plus z is equal to 1/3. 2/3 y is equal to 5/3, and there's no z for that one. So looks like we might have a chance at some sort of solution here. Let's see if we can, we got y at least, right? So y is equal to 5/2. Now we got 5 halves there, but minus x plus 1/3 y, which is equal to 5 halves, plus z is equal to 1/3. So this, unfortunately, let's see, 1/3 minus 5/6, 2/6 minus 5/6, 3/6, 3/6, 1/2, negative 1/2. Is that right? Whew, that was hard. We have this equation, which unfortunately doesn't give us a solution. And if we try to do the same thing with the first one, we got 3w plus 3x plus y is equal to 1. So the only thing that we got out of there is y is equal to 5 halves. So 1 minus 5 halves, negative 3 halves. Well, we could solve for z, but then we still have an x in there. You know, we can solve for x here, but we still have a y in there. So it's kind of messed up that we can't solve for each of these things. And that's the point is that there's not just one solution. That's what I was trying to say. I was trying to say it without trying to say it. Well, it's also now it's also a little bit more difficult to visualize. What we have here is our situation is that we have these aren't just 3-dimensional planes, these are 4-dimensional planes because we have 4 variables. So imagine you're in 4-dimensional space, and then you have 3 4-dimensional planes in 4-dimensional space. Now, if you're getting a picture out of that, then then you're either a genius or you're on drugs. Because you can't picture it. You can't picture 4 dimensions. So can't visualize 4 dimensions unless you're a genius or on drugs. So for this, we're just going to have to try to imagine what's really happening. And we have 4 of these things that are kind of intersecting. Now, it would be interesting for us to figure out, is the intersection going to be something in 2 dimensions, in 1 dimension, or in 3 dimensions? Is it going to be, it's not a point, clearly, because we're not seeing a point here. If we were to see a point, then we would get a value for each of the x, y, and z, and that's your vector, that's your point of intersection. And it's not that. Is it going to be a line in 4 dimensions, a plane in 4 dimensions, a space in 4 dimensions, or what? Because it's possible that it's actually a 3-dimensional space in 4 dimensions. Now, see, if you guys are still trying to visualize that, then you're going to hurt yourself. So, because a space in 4 dimensions is just 1 dimension lower than what you have. So a plane in 3 dimensions is it's a 1-dimensional object. It's an object that's 1 dimension lower than your current space that you're in. So if you're in 3-dimensional space, a 2-dimensional space is a plane. So here you're looking at, if you're in 4 dimensions, your possibilities are you either intersect at a point, in which case you would be able to find w, x, y, z here. You're going to intersect in a line, which I think is going to happen here, but we'll see how that's going to happen. or it's going to intersect in a plane, in a two-dimensional thing, or it's going to intersect in a three-dimensional thing. Okay? All right, so let's think about our situation here and see how we can deal with this. So we're still interested in finding solutions, and I think there is going to be a solution here, which means this is, what is this? What kind of system is this? I kind of went ahead of myself. Consistent, thank you. So a consistent system has at least one solution. And it usually has one solution or has infinitely many solutions. And then when you start thinking infinitely many solutions, that's when you start thinking, okay, is it a one-dimensional solution, a two-dimensional solution, or what? So that's what we're going to try to figure out now. Okay? So with me on that? All right. Well, in any case, whether you're with me or not, we're going to move on. So what we're going to do is our first shot. So we got this. We got the y, right? Y is going on, so y's got a value. So we got a value for that. We're done. Now we have x and z, and then we're going to have x and w later on. But this is our first equation that did not give us a definite value for one variable. So here we have a relationship between x and z. What you're going to do, or one of the things that you can do, is you can let your z equal to a parameter, let's just say t. So your x then can be written as x can be written as a function of t. So x is equal to, I have to bring the t over to the other side, and then I have to take the negative of that, so it'll be positive t plus a half. Is that right? Did I do that right? Okay, now our other equation that doesn't have its own distinct value is 3w plus 3x. Now we already have a value of x here that we can use. So let's take advantage of that. So still our t is equal to z, but our x is equal to t plus 1/2. We're going to write 3w plus 3 times x, which is t plus 1/2, is equal to negative 3/2. And with some fancy math, you're going to get whatever it is you're going to get. W equals, can somebody just tell me? Really? I have to do it? Minus t? Nice. Okay. Oh, there's too many things that are boxed here. What if I get my red pen? So what should it be? I want W by itself, and so something. So W equals. Yeah? All right. So I was over boxing, so I'm going to take a different color pen and box what I really need to box. So I want a value for W, for X, for Y, and for Z. Because those are my variables, right? I want an answer for that. Now, I wasn't able to eliminate one of the variables, or there was an equation where I had two variables, and so they were kind of stuck together. And so I said, okay, wait a minute, I'll just let Z equal to T, and then go from there. So in all these box places, T is a parameter. If I let T equal to any number I want, I should get a W, X, Y, Z solution that's going to work for my system. Does that make sense? If I let T equal to 0, this page is getting long. If I let T is equal to 0, my first variable is W, is going to equal -1. My second variable is X. That's going to be 1/2. My third variable is Y. Well, that's always going to be 5/2. And my fourth variable is Z. Well, Z was equal to T, so T is equal to 0. So this is a solution that will work for my system. That means if I put 1 in for W, 1/2 in for X, 5/2 in for Y, and 0 in for Z, in my original system of equations, I'm going to get all these three equations to be true equations. Okay? So Hal said it was a consistent system. That means I have one solution. Do I have another? Can I have another solution? What if I let T equal to 1? What if I let T equal to 1/2? What if I let T equal to whatever? So how many solutions am I going to have? An infinite number of solutions. A what? A line. What's a line? A line? What do you mean a line? Juan said a line. What's he talking about? I mean, he's right. Yeah, remember that in your quiz? Was that a quiz question or something? W, X, Y, Z is equal to. Now let's see how I'm going to phrase this. Let's try this. Why don't I tell you how it might look like, and then you kind of tell me where the pieces came from. -1, 1/2, 5/2, 0. Where did those come from? This when T is equal to 0. And what's your direction vector? -1, +1, 0. Okay, no more talking, Jamie. Last one? I don't know. Where am I getting this from? Coefficients of T. So, let's talk about where they came from. This is when T is equal to 0. So in all these things, in all these red boxes, when T is equal to 0, your W is equal to -1. When T is equal to 0, your X is equal to 1/2. Well, this has no T. So that's just 5/2. And when T is equal to 0, Z is equal to 0. All right? Now, this is these are the coefficients of T. So for the W, the coefficient of T is -1. The coefficient of T is +1 for X. Now, there's no T here. What's the coefficient of that? That's 0. And then the last one, the coefficient of T is 1. So what does that look like? It's a line. Point plus t times the direction. So we have a one-dimensional object as the intersection of these three, whatever they are, four-dimensional planes. Okay, so this is our solution. Pretty cool, huh? Jane.
So we know our solution sets of plane, if at the end we couldn't get all of them dependent on just t.
Right.
So another variable.
Yeah, so if at the end here, where you might have a relationship between three variables that you can't break apart, then you're going to have to introduce another parameter s, and then you'll have a plane, a two-dimensional plane in 4 dimensions. Ooh, sheesh. All these dimension talk. So it's kind of, you kind of have to peel yourself away from looking at lines and planes now, just taking a look at a dimension of an object somewhere. Tyler?
Would you do the same thing with the echelon diagonal or whatever it's called?
Echelon?
Echelon.
Yeah, as long as you got the echelon form, then you can get started with this business. You write your equations like this, and then from here, try to figure out how to write those relationships. All right. Did you guys fill out those ribbons? Did you walk around the courtyard and fill out ribbons and stuff? Well, I was trying to figure out what to do for mine. I can what? I have to say I can something. I can math. Yeah, that's what I was going to do, huh? I don't know about that.
40. Oh, whatever. I was gonna reuse the matrices in the matrix joke.
Oh, go ahead. We got another 30 seconds here. All right, so we're kind of doing this process already. So we're kind of doing examples and then going back and finding their definition. So let's give that a name, what we've been doing. So when we reduce our matrix, to row echelon form, we that whole process is called Gaussian elimination. It's almost like the addition method when you were just stuck in two variables back in algebra. But this is the actual process is officially called Gaussian elimination, and here's the process. We already did it, so you can copy it from your notes, or I got it directly from the book. And then we did this, leading variable buzz. Okay. Oh, so this one involves two parameters. Let's do this one. I was going to try to find an example in the book or in the homework. Should we get an example from the homework? Yeah, let's see. We are in section 2.2. All right, let's take a look. First of all, there's 5 variables, and then there's a bunch of fractions. You really want to do this?
You have to,
I have to.
Well, and their choice was go hardcore.
I think we.
It's hardcore.
All right, well, let's see. Let's write this in matrix equivalence. So 1, 2, 3, 4, 5. So this is going to be a 3 by 5 with an augmented column. You got a half, a 1, minus 6. Don't forget the zeros, right? When there's zeros, it's nice if it was written this way. If it's not written this way, you have to watch out for those variables to see where the zeros are supposed to be. 1/6, 1/2, 0, -3, and 1. 1/3, 0, -2, 0, -4, and 8. This is going to be easy. No. It can be done there. It could be done with a lot of different things. And you could use Wolfram Alpha and do everything you need to do. You can go to Wolfram Alpha and have it do your laundry. All right, so I'm going to see if I can take a couple of steps at once, and maybe you have to watch out and make sure I'm doing things correctly here. I'm going to change my row 2 by multiplying 1/3 from row 1, and then making sure it's a negative so that they cancel, and then I'll replace row 2. And then I'm going to do row 3 also to get that bottom one. So row 1 isn't going to change. I suppose if I don't want to deal with fractions, I just multiply by 2, right? Oh well, I'm already. Yeah, multiply the whole thing by 6, and then you're. Oh well, we're going to deal with fractions. So the first one, I know that's going to be 0. So let's see, -1/3 plus 1/2. 5/6 or 1/6? Positive, negative, positive. 1/6. -1/3, positive 1/3. -1/3, positive 2, plus 3, -1. 1. -2/3, minus 1, 4, 6, 5/3. -5/3. That wasn't so bad. Now, I'm going to do this here too, so I'm going to want to change my R3. I'm going to multiply R1 by 1/2 to get 1, nope. Yeah. I got an idea. Let's use Wolfram.
Oh,
No, no. No.
well, that would be cheap.
All right. 3/2? No. 1/6? Damn it. Wolfram it is. Wolfram Alpha is Mathematica. Yeah. So we'll play the reduced row echelon form, also known as RREF in Wolfram alpha. Matrices are lists within lists, and the lists go by rows. So a list in Mathematica is in curly brackets. So I'm going to put curly brackets for the whole matrix, curly brackets for the first row, which is 1/2, 1, -1, -6, 0, and we'll throw in the augmented part. That's the first row. Close it up with curly brackets. Open up another curly brackets for the second row. 1/6, 1/2, 0, -3, 1, and then the augmented part is -1. Close the second curly brackets. Open up a third curly brackets. You got 1/3, 0, -2, 0, -4, oops, and then 8. Okay? So press enter and get your answer. Oh, so this is not just row echelon, it's going to be a reduced row echelon. So there's going to be an attempt for Wolfram alpha to make the diagonals equal to 1 and to clear out all the zeros on top if it can. Okay. So here's what we got. Let's just, for your homework, this is okay. Or you can use your calculators too, right? You guys have matrix stuff in your calculators.
Oh, and there's a row that is full of zeros and is equal to 0.
Oh, we got a whole row full of zeros equal to 0. Probably. Well, the important thing to note is that the whole row is full of zeros, and if you look at the augmented part, you got zeros equal to 0, which is a good thing. It means you're going to have, this is going to be consistent. By the way, if you row reduce it and you got a 0 and the augmented part is non-zero, then it's inconsistent. We didn't do an example like that, but if you were here watching the video before I came in, that was one of their last examples. Yes, it's possible if the lines are inconsistent. If they don't have a solution, then you're going to have row zeros equal to non-zero number, and then there's no solution. So this one will have a solution, and we will rewrite our system into 1 times x1 minus 6x3 minus 12x5 is equal to 24. We got 1 times x2 plus 2x3 minus 6x4 plus 6x5 is equal to 10. Minus 10. Thank you. So, these are the leading variables, leading coefficients, the leading terms, and then they both have a 1, which means all these other values over here, all these other variables here have to be represented by a parameter. What does that mean? That means that we have to let x3, red, x3 equal a parameter, x4 equal to a parameter, x5 equal to, what comes after s? T, U. Oh, R, okay. That's backwards, huh? All right. Should we should probably switch it. Okay. So is not in order. Damn it. R. Oh, I'm using the wrong pen. I'm flustered now because it's time. Now let's finish this. So you usually want to write your vector x1, x2, x3, x4, x5. And then it involves some constants. So the idea is that, I'm not doing all the steps here, but the idea is to bring everything else on the other side. It's going to involve a constant, and then the multiples, the coefficients of x3 of r, the coefficients of x4, and the coefficients of x5. So the constants are 24, negative 10 for x1 and x2. And then all these other ones will have zeros because their relationships won't have, these are the relationships here. So x3 is going to equal to r, x3 is going to equal to r, x4 is going to equal to s, x5 is going to equal to t. And those are the coefficients of r, s, and t. And when you bring these terms to the other side, their coefficients will change, right? So for x1, the x3 coefficient is going to be positive 6. Oh, I'm sorry. Is that right? Yeah. The x4 coefficient would be 0 because there's nothing there. And the x5 coefficient would be positive 12. The signs will change. For x2, this is going to be negative 2. This is going to be positive 6. And this is going to be negative 6. And then the relationships for x3 now is just r, s, and t. And x3 will not have any other variables associated with it aside from t or from r. And x4 won't have any variables associated with it aside from s, etc. So your final solution should look something like this. So how many dimensions is this? It's in a 5-dimensional space, but your intersection is a 3-dimensional space. All right? So next time we're going to look at those dimensions a little closer and give them names. All right, that's it. Goodbye. Oh, wait a minute. Now that you guys are experts in MATLAB or FreeMat, whoops. Your worksheet will be going through and setting up matrices and doing some row reduction for the matrices. So you're going to set up a matrix. We're going to, yeah, it's right here. So this is your worksheet, your HbA2. A week from today. Yeah.